the first part of our lesson this week, we learned about the modulus and the argument of complex numbers. Today, we will learn what those two are exactly for. We said that we would have 3 targets for this week, and we were able to achieve the first 2 targets in our class. Today, we are going to achieve the third target, that is to convert a complex number in rectangular form to polar form and vice versa. Let's start with the first part of our target. A complex number z can be written in 2 forms, the rectangular form and the polar form. We have previously learned about the rectangular form. It simply is the form z equals a plus bi. From this, we can obtain the modulus r of z, which is equal to the square root of the quantity a squared plus b squared. On the other hand, the argument theta of z is equal to tangent inverse of b over a. We also have to check where z is located in the graph to be accurate with the argument. Since theta can be negative or sometimes greater than 360 degrees or 2 pi radians, if we restrict it to be between 0 and 360 degrees, then we call it the principal argument of z. In this figure, we see the complex number a plus bi with its modulus r and argument theta. Using our SOHCAHTOA relationships, we see that cosine theta is equal to a over r. This yields a equals r cosine theta. We also see that sine of theta is equal to b over r. This in turn yields b equals r sine theta. Logically then, if z is equal to a plus bi and a is equal to r cosine theta and b is equal to r sine theta, then z is now equal to r cosine theta plus I r sine theta. Factoring r out, we have z is equal to r times the quantity cosine theta plus I sine theta. Most of the time, we use the shorthand notation r cis theta to denote this, where c is for cosine, I is for the square root of -1, and s is for sine of theta. This is what we call the standard polar form of complex numbers. Let us practice writing complex numbers in standard polar form. Let's say we will write 4i minus 4 in standard polar form. It would be helpful if we rewrite it to a plus bi, so we have -4 plus 4i. Thus, a is equal to -4 and b is equal to +4. Solving for the modulus r, we have the square root of the quantity a squared plus b squared, or that is the square root of the quantity -4 raised to 2 plus 4 squared, or when simplified, that is 4 square root of 2. Meanwhile, solving for the argument theta, we have tangent inverse of 4 divided by -4, or tangent inverse of -1. That will give us -pi over 4. But since we are writing it into standard polar form, theta must be between 0 and 2 pi or 0 and 360 degrees. We also know that the complex number is located in the second quadrant. Thus, we have theta is equal to 3 pi over 4 or 135 degrees. Now that we have the values for the modulus and the argument, we can simply write our 4i minus 4 in 2. 4i minus 4 equals 4 square root of 2 times cis 3 pi over 4, or 4 square root of 2 cis 135 degrees. We can also write a complex number from the polar form into the rectangular form by evaluating r cis theta. For instance, here we will write 3 cis 4 pi over 3 in rectangular form. We can evaluate this, and then we will have 3 times the cosine of 4 pi over 3 plus I sine 4 pi over 3, which is now equal to 3 times the quantity -1/2 minus the square root of 3 over 2i. Simplifying this further, we get -3 over 2 minus 3 square root of 3 over 2i. This is now in the form a plus bi, or the rectangular form of a complex number. At this point, we will also introduce ourselves to the polar coordinate system. Unlike the Cartesian coordinate system, which uses the x and y coordinates to locate a point, the polar coordinate system uses angle measures and directed distances to locate a point. The fixed ray from which we will generate our angle is the polar axis, or the polar line, and the fixed point is the pole, or the origin. Every point may be assigned polar coordinates r, theta. R is the directed distance between the pole and the point, and theta is the angle from the polar axis to the segment joining the pole and the point. In this example, A is assigned the polar coordinates 3 and pi over 3. That means that the distance between the pole and the point is 3 units, and it takes pi over 3 radians to reach the segment joining the pole and the point from the polar axis. We thank the developers of the GeoGebra app, which we use tremendously in drawing the graphs in this video.